Alright, I want to go over a couple more practice problems for Unit 6, which is radical reactions. So this video is 06M30. Just a reminder, I did summarize all of the reactions in a type of roadmap in a previous video, 06M20. The main point of this video, the previous video, was to show you how many ways Br2 can be used, and if you're not careful about observing what the starting material is, you may be doing the wrong reaction using Br2, because just as a review, Br2 could be used for halogenation of alkenes, allylic halogenation of alkenes, and radical halogenations of alkanes. Okay, and not only that, if you take a look at the roadmap from this video, there were also some reactions using Hbr multiple times. Okay. Oh man, I totally forgot about halohydrin when you have Br2 and water. Okay. If those reactions are not rolling off your tongue and they're not easily accessible in your head, then please go back and watch the video on this roadmap 06M20. But for this video, I'm going to show you a couple of exam problems that that I may put on my exams, and it looks like we're going to have some examples of mechanisms, including a mechanism showing resonance. Okay. Alright, I already wrote out the first problem. Let me just circle this. Okay. You want to read the directions carefully because you don't want to do extra work if you don't have to. Here it says draw the correct products. Okay, it could be one product or it could be multiple. Do not use wedge dash drawings. So it seems like this question is not, or this problem is not concerned about stereochemistry. And then here it says if an alkene or allylic halide, which has a carbon-carbon double bond, as you know, if either of those that you draw has cis-trans isomerism, just draw one or the other. You do not have to draw both, the cis and the trans. Okay. So that simplifies things a bit. You don't have to worry about drawing the trans if you do the cis. Okay. Let's start out really easy. All the problems will be in black, and then my work will be in green and pink, and my final answers will be in blue. Okay. I'm going to write out all four. Looks like four, maybe three. All three of these reactions. And you could definitely pause the video and copy these. Maybe do 5. There are 5 reactions. You could definitely pause the video if you want to copy all of these now, or you could copy them as we go. One of these actually is not a reaction in Unit 6, but I added it to show you that you don't want to get confused. For instance, on a final exam, when you combine all the units, you're going to have to know all the reactions in the context or in relationship to each other. Okay. Remember, in pink and green are going to be my notes or annotations. In blue are going to be my product, my answer. You know, when I see this, I definitely see an alkane. And there's only one reaction that you could do with an alkane, at least the way I teach organic, and that's radical halogenation. And you are going to put the Br on the most substituted carbon that has a hydrogen, because you are replacing that hydrogen. Don't forget that methyl group. Okay. So you just can't plop a Br right here, because you're going to lose that methyl group if you do that. You have to draw a new bond to the bromine, because what happens in this reaction is that you form a tertiary radical. You notice that you can't form a radical on the right because there's no hydrogen to it, what's called abstract. In this mechanism, you abstract a hydrogen to make a radical. Okay? I'm trying to emphasize that there's only one reaction you can do with an alkane, because later on, when you do synthesis, you're hoping for an alkane starting material, because that's 3 points. All you have to do is draw these reagents and draw your product. The other thing is that for some classes and some professors, it'll be very important that you understand that this is the chiral carbon and you get wedge and dash. But again, we are not going to use wedge and dash in this example here. Okay. What is this? Oh, why don't I name these reactions also? Right? Radical halogenation of an alkane. Okay, I gotta go a little bit faster because I do have some problems that I do want to show on this video. So this one is allylic halogenation, because we have an alkene. The type of reaction switches when you go from an alkane to an alkene, but our reagents are the same. I could have used heat, okay, Br2 and heat. The thing about this is that we have two allylic positions. But you notice that if I put the radical here, it's the same as putting the radical here. All you have to do is rotate the molecule and you get the same looking radical. So there's only one type of radical, and we'll call those A. The problem is you have resonance, and so this is still in pink. My initial radical looks like this. Okay. And then I'm not going to draw the mechanism for the resonance. I'll do that later. But simply just shift the double bond, and our new radical looks like this. That's where I'm going to put the bromine, where the radical is. Okay, and it looks like they'll give us two different products. So I'm going to go up, and I'm going to draw one of the products like this. See, that's an allylic halide, because we are doing allylic halogenation. So that makes sense. What about the other one? Yep, that's also allylic, right? The bromine's on the allylic position. These two reactions are the same. These two reactions are the same. Either you could use Br2 in light, or you could use what's called NBS, N-bromosuccinimide. So these are both allylic halogenation. You could always refer back to your notes or look in your textbook to do some more reading on that if you're not up to speed with this. Okay. Sometimes I ask for the mechanism, sometimes I don't for allylic halogenation. Typically in summer classes where it's kind of condensed and we're moving really, really fast, I don't have students memorize the mechanism for this, although they need to know what kind of radicals they make. Okay. So here we only have one allylic position, and I'm going to try to do this without drawing the intermediate radical and its resonance. So the first product, all you have to do is plop your bromine where that radical is. Okay. And we could mark this up. Okay. Let's say we make a radical there. Think about the resonance. The resonance would look like this. The double bond will shift. The radical will be on the N carbon now. That's where my bromine goes. By the way, this should have a plus. It's not this or that. It's a mixture of this and that. I should have also said circle the major product. Yeah. Let me do that. Circle major. Circle the major product if there is one. The thing is, we only have one product here, so obviously that's the major. When you have allylic halides, you're choosing the major product based on the stability of the double bond. Since both double bonds are di-substituted, it's okay not to circle a major product, because the rules that I've given my students, there's no way to decide which one is the major product, because they're both di-substituted. So here it says circle major product if there is one. So it's okay not to circle, and I would expect none of these two to be circled, but this one, di-substituted. The alkene is di-substituted versus mono-substituted. This is actually a Unit 5 problem. Unit 5 problem. It's Markovnikov addition of Hbr. So your Br goes there. But in Unit 6, by adding peroxides, we have non-Markovnikov addition. Non-Markovnikov addition. So instead of putting the bromine here, the carbon on the left of the double bond, we're going to put the bromine here on the right carbon of the double bond. Okay, good. Those are fill in the products. Okay. I'm showing you what literal notes I would be taking if I were a student taking the exam, and I'm also trying to do this in real time to show you the speed at which you would want to know how to do these problems. Okay, so again, let's just scroll. You could always pause and test yourself again. Number 2, I pre-wrote the problem also. For the allylic halogenation below, draw the products that come from the most stable radical. Good. Then circle the major product. Do not worry about cis-trans isomerism. I'm telling you that it's allylic halogenation. We've seen allylic halogenation here twice, okay? But why am I setting this question 2 apart from here? Because in the example that I'm going to show, we're going to have multiple allylic radicals that are possible. I purposely labeled all of these A because these two are identical. Whether you have the radical here or here to start with, you will still get the same 2 products. Over here you only have one allylic carbon, so there's only one allylic radical possible. But just remember, due to resonance, you get 2 products. Take a look at this one, and we're going to analyze this together. So, NBS tells you you're doing allylic halogenation, but now we're going to do our analysis. That's allylic, That's allylic. Right? It's the carbon off of the double bond, and this is allylic. Okay? But I'm going to say, you know what? Let's make this easier. Okay, now it's obvious. Do you see what I did? Now it's obvious that these two are identical. Okay, regardless of, interesting. I know some of you are saying, well, no, one is cis to this carbon and one is trans. But as you do resonance, you're going to lose this double bond anyway, or this double bond is going to shift anyway. So it wouldn't matter whether that carbon is cis or trans to either of these two carbons. Yeah, so this turned out to be a little more complicated than I thought, but the main point is you have two different places to put the radical. The A, which I'm going to say these two A's are identical, and the B's. Okay, and the B. Let me see if I could fix this to make it super symmetrical. I'll just leave it like this. The main point is you want to draw your products from the most stable radical. Okay, so this takes a little bit of scratch work, and if I'm going to ask this on an exam, I will give them space, my students space to do the scratch work. Let's see. Let me just see if this radical, when resonance happens, if these two are equivalent. So our first radical, I'm going to put it where the top A is, and then what is the strategy? Draw the resonance. Okay, I have that. I think that's good news, because now that this is a single bond, this methyl group can rotate, making these two carbons actually within the mechanism identical to each other. Okay. Let's do part B. What if there's a radical on this end? See, the problem is asking to draw the products from one of these two radicals. Some of you are saying, what do you mean two radicals? It looks like you have four radicals. Not technically. Let me just double check this. Yeah, let me change this, because the two radicals that I'm looking at are almost of equal stability. Let me put, and you could do this. Let's put another methyl group there. Easy fix. Methyl, 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 and again, it doesn't matter cis or trans. Methyl. Okay. You'll see why in a moment why I wanted to add that methyl group. But let's go back to the idea that we only have two radicals. We have the radical coming from A because, remember, resonance, it's not this half the time and this half the time. It's these two all the time. It's this hybrid all the time. So the actual radical is a combination of this. So when I say radical A, I mean the combination of these two. When I say radical B, I mean the combination of these two. And when I ask for the product from the most stable radical, you are choosing either situation A or you're choosing situation B. And do you remember how to do that? You look at the type of radical you have. You have secondary allylic. And actually all of these are allylic. Here we have secondary allylic. Here we have secondary allylic. Tertiary allylic. I'm not saying that this is the winner. I'm saying the combination of these two are the winner. So what I'm going to say is radical B is the winner. And that's how you're going to draw your products. You're drawing it from radical B. Just like here, you see these dotted blue lines? We drew the products from the two radicals from radical A. There is no radical B because this radical here, or the potential radical here, is identical. Okay. So these are your two products. Yeah, and I'm hoping there's a major product after we draw the two products. Yes. Okay. Alright. Test yourself. Well, first of all, do you see how I drew the products from these two resonance contributors? Okay, two resonance contributors. Technically, they are the same radical because they are both true or acceptable representations of the hybrid. Okay. Which one's the more stable? Allylic halide. This one's tri-substituted. This one's only di-substituted. The major. Okay. Next thing. Problem 3. Problem 3, let me do resonance. So this is draw mechanism arrows. To get a new resonance contributor. And obviously you have to draw not only the mechanism arrows, but also the contributor. Okay. I'm going to give us a pretty interesting one. It's going to be benzylic. A ring that looks like this, a 6-membered ring with 3 double bonds. That's called right there. That's called benzene. And if you have a carbon off of that ring, that's called a benzylic carbon. So this is a benzylic radical. Technically, it's a tertiary, right? Tertiary benzylic radical. Okay. So whenever you did resonance, for instance up here, all I did was shift the double bond and put the radical, the unpaired electron, on the carbon that got naked. See, this carbon here has 4 bonds, but when I shifted the double bond towards the radical, it now only has 3 bonds. You gotta know that there's only 1 hydrogen on this carbon. But how did that happen? If you didn't understand why I could shift the double bond and get the radical on the other side, this is why. You're going to take this unpaired electron and you're going to draw a fishhook, and we're going to start making a double bond right here. You're going to take this pi bond. Okay, I would want to draw it underneath here, but it's kind of crowded. Okay, so I'm going to go on top. It's still the same thing. What am I announcing to do? I'm putting 2 electrons between these 2 carbons, so the double bond is right there. But this pi bond has 1 other electron. You're going to put it on that carbon. That's why it works that all you have to do is shift the double bond towards the radical and put the unpaired electron on the carbon that got naked. The other 2 double bonds are good. Now, I'm not going to draw the other contributors, but you could imagine, right? You could imagine now this double bond shifting. And then you can imagine this double bond shifting. But I only asked for a new contributor, so I'm not going to draw the other 2 contributors. Okay. So that's number 3. Number 4, and this will be the last problem. All the exams at this point in the semester will have mechanisms. We saw mechanism for resonance, but what about the mechanism for a reaction? So, number 4, draw the mechanism. Easy. Well, I spelled it wrong. Draw the mechanism. We had we had a radical halogenation as the first problem. Remember that? Okay. This one right here. Alright, so the product we know already. We just are now tasked with drawing the mechanism. Okay, it's kind of a big molecule, but we could do this. Initiation. If you've studied your notes already, okay, why don't you pause the video and see if you could do the mechanism before you see me doing it. Fish hooks. Go ahead and use a little pulse of light. And I know it's not necessary, but I like to draw both bromines. Okay. You could draw the radical as an unpaired electron, or you could fill in the other lone pairs if you want. Those are identical, and they're both neutral. Propagation. Propagation, you got to remember one radical, one non-radical. So here's my non-radical, the alkane. Here's my radical, the bromine. Did you see what I did? I have to show explicitly the hydrogen ion abstracting or removing. I'm removing this because I want the tertiary radical. I say meet in space to bond the hydrogen and the bromine, and then take one electron in the bond and put it as the unpaired electron. There's a radical, and we did create Hbr. Yeah. Second propagation step. Take your radical that you just made. Don't take Br radical, okay? Because this is propagation. We have to make a product that can recycle back. The product that can recycle back is going to be a bromine radical. So how do I draw the arrows here? Meet in space. Okay. There. I get my product. Great. And I get this bromine radical that can recycle back. Here. Okay, you don't have to draw the green arrow in a formal mechanism problem. Oops, do you see that? Yeah. Actually, I shouldn't have drawn that. But you get the idea. The bromine can come back and start the process over again. This is a great technique because it keeps going and going and going, hopefully until all your alkane turns into alkyl halide. But there are processes that cut this chain short. Or not the chain, but cut the reaction short. But some of the steps aren't that bad. Like for instance, the combination of these two radicals. So termination is between two radicals. This is not bad because we could always hit it with another pulse of light to start at the beginning again. Okay. And also this is not bad. It's not bad, it's just long to keep drawing these termination steps. Okay, so we do get the product. Beautiful. The thing is, when you have too many radicals, you're going to have too much of this at the same time. And this is what we really want to try to avoid. Once we make the product here of these two coming together, there's really nothing we can do to get anything close to this product. So we didn't hit our target. And not only that, this is kind of hard to draw. So we have a bond to the other ring right there. That ring has a alpha group and bunny ears. I'll draw them to the left. Doesn't matter because this can rotate. And the bunny ears here are there. The idea is that you have double the amount of carbons that you had for each of these. So there are 8 carbons here. 8, there should be 16 carbons here. So that's the full mechanism for radical halogenation, starting with initiation. Okay. Practice, practice, practice. You could always cover this up and recopy each of these problems that are in black.